Hi, I'm Jaejun Lee, a PhD student of School of Computing at KAIST. I'm a member of the Big Data Intelligence Lab led by Professor Joyce Jiyoung Whang. I will explain our paper, PAC-Bayesian Generalization Bounds for Knowledge Graph Representation Learning, presented in ICML 2024. Knowledge graphs represent human knowledge using triplets, each of which consists of a head entity, a relation, and a tail entity. For example, the fact that Vienna is the capital of Austria is represented as Austria, capital Vienna. However, real-world knowledge graphs do not exhaustively represent all known facts. To find missing triplets in knowledge graphs, we need a model that can tell if a given triplet is true or false. For example, USA contains Vienna is false, whereas British Columbia official language English is true. Like this, the task of triplet classification is to classify a triplet as true or false. Knowledge graph representation learning, or KGRL for short, has been considered one of the most effective approaches for triplet classification. Given a knowledge graph, KGRL methods learn representations of the entities and relations in the knowledge graph, which are used to compute the score for a given triplet. Based on this score, the plausibility of the given triplet is determined. While KGRL techniques are widely used in many real-life applications, theoretical analysis of their generalization ability has been rarely conducted. Given a model, we can measure its generalization error by the difference between the losses calculated on the full set E and the training set E had. If we can find the theoretical upper bound of a model's generalization error, known as the generalization bound, we can measure the model's generalization ability. The smaller the generalization bound, the better the generalization ability. In this work, we present the first PAC-Bayesian generalization bound for KGRL methods, which provide theoretical grounds for commonly used tricks in KGRL and guide desirable design choices for practical KGRL methods. PAC learning theory provides fundamental tools for analyzing the generalization bounds. There are several PAC-based approaches, such as VC dimension-based, radiomature complexity-based, and the PAC-Bayesian approaches. Among these, we use a PAC-Bayesian approach, as it has been known to provide tighter bounds than the other approaches for the generalization bounds of GNNs. The PAC-Bayesian generalization bound relies on the KL divergence of a posterior distribution from a prior distribution. A prior distribution indicates prior knowledge about a given problem that is independent of the training set, while a posterior distribution is learned by a learning algorithm using the training set. By computing these distributions, we can calculate the generalization bounds. The original PAC-Bayesian framework assumes that the training dataset is independently and identically sampled from an infinite and continuous data distribution. However, in triplet classification, the full triplet set is finite, and the training triplets are sampled from the full set without replacement. Therefore, we use a transductive PAC-Bayesian framework, which assumes that the full set is finite. To comprehensively represent and analyze various KGRL models and their possible variants, we designed the relation-aware encoder-decoder framework, READ in short. The encoder in READ is called Relation-Aware Message Passing Encoder, or RAMP encoder. Our RAMP encoder is a comprehensive neural encoder for KGRL that learns the representations of entities by aggregating representations of the neighboring entities and relations. The triplet classification decoder in READ uses the representations to compute the scores of each triplet for determining whether a given triplet is true or false. Depending on how the interactions between entity and relation representations are modeled for computing the scores, we design two decoders, the translational distance decoder and the semantic matching decoder. The READ framework assigns two different scores for each triplet. SWHRT0 is the score proportional to the likelihood of HRT being false, and FWHRT1 is the score proportional to the likelihood of HRT being true. Our RAMP encoder can subsume the KGRL methods that employ GNNs or MPNNs. In the RAMP encoder, the neighbors of each entity are defined per relation. For example, we consider different neighboring entities for the entity Canada based on the relations member of, part of, official language, and country. The connections between entities with relation R can be represented using a graph diffusion matrix SRL. To update on entities representation, we first gather the entity and relation representations of its relation-specific neighbors. Once we obtain the representations of the neighboring entities and relations, they are projected using relation-specific projection matrices. This way, we can consider different perspectives of a neighbor entity based on the relation it is connected by. Finally, the projected neighbor representations are aggregated to update the target entity's representation. Here, the type of aggregator is represented by the diffusion matrix. For example, when the diffusion matrix is set to an adjacency matrix defined for relation, it represents a sum aggregator. On the other hand, if the diffusion matrix is set to a degree normalized adjacency matrix, it represents a mean aggregator. The relation representations are updated using a projection matrix that is shared across all relations. Since the ramp encoder is formulated to represent the aggregation process in a general form, several well-known GNN-based KGRL encoders can be considered special cases of the ramp encoder. For example, our ramp encoder can represent RGCN. Instead of considering relation representations, RGCN only considers relation-specific projections of the entities. Also, the graph diffusion matrix in RGCN is an adjacency matrix normalized by a problem-specific constant. The problem-specific constant CVR is usually set to the number of neighbors of entity V connected by R, meaning that RGCN uses a mean aggregator per relation. WGCN is also a special case of our ramp encoder. WGCN uses the sum aggregator, and it also does not consider the relation representations. Instead of learning separate projection matrices for each relation, WGCN utilizes a relation-specific constant, alpha RL, to generate relation-specific projection matrices from a shared projection matrix. CompGCN can also be represented by our ramp encoder. CompGCN's aggregator is a sum aggregator, and it uses relation representations. The relations in the same category share the same relation-specific projection matrix. By using the opposite sign of the relation-specific projection matrix for entities as the projection matrix for relations, we can represent CompGCN with subtraction operator. In summary, our ramp encoder can represent RGCN, WGCN, and CompGCN by appropriately setting the activation functions, projection matrices, and diffusion matrices. This table shows how we should set the activation functions phi, rho, and psi, as well as the projection matrices WRL, URL, and the diffusion matrix SRL to represent each model. For further details regarding each term, please read section 3.1 and appendix B.1 of our paper. To calculate the scores of each triplet, we define two types of triplet classification decoder. The first one is the translational distance decoder, TD decoder in short, which computes the scores of a triplet HRT by measuring the distance between H and T after relation-specific projections and a relation-specific translation is carried out. For example, to calculate the scores of British Columbia, official language English, we first project British Columbia and English using the projection matrices of the relation official language. We then translate the projected British Columbia with a relation-specific translation. Finally, we measure the distance between the translated British Columbia and English to calculate the score. Similarly, we can calculate the scores of the triplet USA contains Vienna by relation-specific projections, translation, and measuring the distance. By appropriately setting W bar Rj, VRJ, and U bar Rj, we can represent existing knowledge graph embedding methods as special cases of our TD decoder. For example, to represent trans E, we set W bar Rj and VRJ to TNSJ and U bar Rj to TRLJ. Trans E represents each entity using learnable vectors, translates the head entity using relation-specific translation, and compute the score of each triplet by the distance between the head and tail entities. We can also represent rotate E using our TD decoder. Rotate E represents each entity using complex vectors, rotates the head entity using the relation vector in the complex space, and then measures the distance between the head and tail entities to calculate the scores. This table shows how we should set the grid projection matrices to represent existing knowledge graph embedding methods. All these methods fall into the project and translate framework of our translational distance decoder. The semantic matching decoder, or SM decoder in short, computes the scores of a triplet HRT based on the similarity between the individual components of the triplet. For example, to calculate the scores of the triplet British Columbia official language English, we measure the similarity by considering the interactions between the head entity British Columbia, the tail entity English, and the relation official language. Our SM decoder can represent many existing knowledge graph embedding methods. One example is RESCAL, which considers pairwise multiplications between the individual components of the triplet. Another example is DistMult, which computes the score of a given triplet by the sum of the Adamar product of the individual components of the triplet. Our SM decoder can also represent other knowledge graph embedding methods, such as whole E, complex, analogy, simple, and quad E. These methods compute the score based on the similarity between the individual components of the triplet. The difference lies in how they define the similarity, which can be generalized using relation-specific matrices U bar Rj. READ can represent many existing KGRL methods, ranging from simple shallow architectural models to neural encoder-based models. For example, using the ramp encoder and the translational distance decoder, we can represent CompGCN with TransE. Similarly, using the ramp encoder and the semantic matching decoder, we can represent RGCN with DistMult. When we do not use the ramp encoder and only use a triplet classification decoder, we can represent the shallow architectural models such as TransR, RotateE, DistMult, and Analogy. This is the list of 15 different published KGRL models that can be expressed by our READ framework. Recall that the generalization error is defined by the difference between the losses measured on the training set E head and the full set E. To measure the loss of a triplet classifier on a training set, we use the gamma margin loss. Gamma margin loss is a loss that is taken into account when the score of the ground truth label is less than or equal to that of the other label with a margin of gamma. When the gamma margin loss is measured on the training triplet set E head, it is referred to as an empirical loss. To measure the loss of a triplet classifier on the full triplet set, we use the classification loss. Classification loss is a loss that is taken into account when the score of the ground truth label is less than or equal to that of the other label without any margin. When the classification loss is measured on the full triplet set E, it is referred to as an expected loss. Based on our definitions of the empirical and expected losses, we provide the transductive PAC-Bayesian generalization bound for a deterministic triplet classifier. Since the PAC-Bayesian generalization bound originally assumed a stochastic classifier, we extend the existing transductive PAC-Bayesian generalization bound to the deterministic classifier. To transform the theorem for a stochastic classifier to a deterministic classifier, we add random perturbations to the fixed parameters of the deterministic classifier. This is equivalent to constructing a posterior distribution by adding random perturbations to the fixed parameters. To present the PAC-Bayesian generalization bound for READ, we make three assumptions. Assumption 1 holds for most activation functions, such as ReLU, leaky ReLU, tangent H, soft plus, and sigmoid. Assumption 2 follows from our problem formulation. Assumption 3 assumes that the training triplet set contains at least 20 triplets, and the full triplet set contains at least 20 triplets that are not included in the training triplet set. All these assumptions hold for most real-world datasets and models. This is the generalization bound for READ with TD decoder. Let's take a closer look at each term that affects the generalization bound. First, the generalization bound increases as the total number of learnable matrices and W increases. This explains the benefit of the parameter sharing strategies in CompGCN and the basis or block decomposition ideas in RGCN, because these tricks decrease the number of learnable parameters. The generalization bound also increases as the number of layers in the ramping quarter increases. Also, the bound is affected by the infinity norms of the diffusion matrices. This suggests that a mean aggregator can be a better option than a sum aggregator in reducing the generalization bound, as the norm of a diffusion matrix decreases when normalized by the degree in the mean aggregator. The norms of the learnable matrices also influence the generalization bound. Larger norms lead to higher bounds, providing theoretical justification for weight normalization used in GNS and normalization of entity representations used in Trans-E. The bound also increases with the dimensions of the representations. Here's a proof sketch of the generalization bound for read. Since a PAC-Bayesian generalization bound relies on the KL divergence, we first assume that the prior and posterior distributions are Gaussian distributions with the same standard deviation. As in the proof of the transductive PAC-Bayesian generalization bound, we construct the posterior distribution by adding random perturbations to a fixed parameter. We then calculate the difference in scores between the fixed parameter and a random parameter in the posterior distribution. This involves a two-step unrolling of each recursion step to consider the interactions between the entities and relations in the ramping quarter. Based on this difference, we calculate the standard deviation of the prior and the posterior distributions, which leads to the KL divergence. Using this KL divergence and covering ball analysis, we derive the generalization bound for read with TD decoder. This is the generalization bound for read with SM decoder. While the magnitude may vary, the increasing and decreasing trends of the critical factors remain the same. The proof is very similar to the previous one. We assume that the prior and posterior distributions are Gaussian distributions with the same standard deviation. Then we calculate the perturbation bound of read with SM decoder and the KL divergence. Using these, we derive the generalization bound for read with SM decoders through covering ball analysis. To empirically demonstrate the relationships between the critical factors in the theoretical bounds and actual generalization errors, we conduct experiments on 3 real-world knowledge graphs, FB15K237, Codex M, and UMLS43. We measure the generalization error, which is the actual difference between the expected and empirical losses observed in a particular experiment. Among the critical factors that affect the generalization bounds, we examine the effect of the type of aggregator, norms of the learnable matrices, and the number of layers in the ramping quarter. First, we compare our read framework using sum aggregator and the mean aggregator. When varying the aggregator, we find that the mean aggregator consistently shows lower generalization errors than the sum aggregator across all datasets and models. We fixed the Frobenius norms of all weight matrices to observe the trends induced by the norms of the weight matrices. By varying the norms of the weight matrices, we observed that generalization errors are proportional to the norms of the weight matrices, which aligns with our theorems. Increasing the number of layers in the ramping quarter also leads to higher generalization errors, confirming the findings in our bounds. We also investigate the impact of the dimensions of the representations. Using one-hot encodings as initial features fixes the maximum dimension to the number of entities. Therefore, instead of using one-hot encodings, we extract the initial features from textual descriptions of the entities and relations to control the maximum dimension. We observed that the generalization errors increase with the dimensions, which aligns with the expected tendency. In this work, we proposed the novel read framework that can express at least 15 KGRL models, including not only GNN-based models such as RGCN and CompGCN, but also shallow architecture models such as RotaD and Analogy. We proved the generalization bound for the read framework, which is the first PAC-Bayesian generalization bound for KGRL methods. Our generalization bounds for the read framework provide theoretical grounds for commonly used tricks in KGRL, such as parameter sharing and weight normalization schemes, and guide desirable design choices for practical KGRL methods. Last, we empirically showed that the critical factors in our generalization bound can explain actual generalization errors on 3 real-world knowledge graphs. Our datasets and codes are available at this link. Also, you can find more materials on our homepage. Thank you!